And welcome, Calculus 2 students. Today we are extending our linear approximations to quadratic approximations, and it's just going to make it a little more accurate, especially when we have a curve that changes slope quite rapidly here at our point A. So we have been finding linear approximations at A, and it works quite well as long as we don't have a lot of curvature here. If we extend this to a quadratic approximation and eventually the polynomial approximation, then what we are going to be getting, it will be fairly accurate in finding those values. In our first example, we are to find an approximation for the natural log of x. So we want a linear approximation, so I've written down what the linear approximation equals. We're going to need this linear approximation at x equals 1. So I'm going to need, since my a is equal to 1, I'm going to need f of 1, and that's going to give me the natural log of 1, which is then going to be 0. I'm going to need to know f prime, so f prime of x equals the derivative of natural log of x is 1 over x. So f prime of 1 is then 1 over 1, which is 1. And I have all the information I need now to get this linear approximation. So this linear approximation we'll call P1 of x is going to be equal to f of a. F of a is 0 plus f prime of a, that's 1, times x minus 1, because my a is 1. The linear approximation is x minus 1. So for the quadratic approximation, which is sitting here, P2 of x is going to be equal to, I'm going to need P1, which is x minus 1, plus, and now I've got to go find these things. So let's get f double prime of x, take the derivative of 1 over x, you're going to get negative 1 over x squared. F double prime of 1 is going to be equal to negative 1. Plugging this in, 1 half, that's going to be negative 1, and then x minus 1 quantity squared. Do some algebra. Right, not much to do, but my C question wants me to do P1 of 1.05, and that's going to be 1.05 minus 1. And so for this one, I will get the value 0.05. For P2, I'm going to plug in 1.05, tell you what I get. All right, there's what we get. Pretty close. Let's see what our calculator gives us if we plug that in. The natural log of 1.05 is 0.04875 and 79, sorry. Can't read my calculator. And if I compare these two, I'll see that the quadratic approximation is better. What Taylor polynomials do is an extension of this thought process of doing the linear and then the quadratic and then the third degree polynomial approximation, fourth degree. You'll notice that the Taylor polynomial expansion does the exact same thing, but it'll tell you it wants you to go to some nth derivative, which is what this one tells you to do. They want you to go to the 7th derivative. So I'll write down those derivatives. And once you find those, because they're wanting me to use an a value of 0, I now need to find f of 0, f prime of 0, f double prime of 0, and etc. Alright, we have about what we need. We're going to start here and find P1. And P1 is going to be f of 0 plus f prime at 0 times this x minus 0. So for this one, I am going to get, looks like 0 plus 1 times x, and that is going to be equal to x. Let's get the second one. The second one is just going to be all of the first, which was x plus this stuff here. So that's going to be f double prime of a. That is 0 over 2 factorial times x minus 0 quantity squared. This once again is going to be x. This is going to change though when I go to P3. P3 is going to be all of P2, which is just x, plus the next one is going to be negative 1 over then 3 factorial and then x minus 0 quantity cubed. So this guy is going to be x minus then x cubed over 6. And I'm going to continue from there. And finishing this up, I did note that every even approximation is going to be what the odd one is due to this 0. And this is what they were looking for. In our next example, we are going to find the Taylor approximations. So the first thing I'll need to do is find those function values and find those derivatives at that x equals 0 value. So I'll do that. Alright, we found those function values. Now we'll need to find P1 of x. P1 of x is then going to be that f of 0, which is 1, plus the f prime of 0, which is 1 over 1 factorial, which is just 1, and then x minus 0, and this is going to be 1 plus x. P2 of x is going to be that 1 plus x, and then it's going to be plus f double prime at that point, which is 1 over 2 factorial x minus 0 quantity squared, and this will then yield 1 plus x squared over 2. P3 is then going to be this whole thing, 1 plus x squared over 2 plus 1 over 3 factorial x minus 0 quantity cubed. And for this one, you will just get that thing plus the x cubed over 6. And here's a table with that number crunching to it. You'll notice that as n gets larger, the error gets smaller and smaller, and we get closer and closer to our values. Our example 4 is another Taylor approximation. In this one, we'll choose our function to be square root of x, and I need to find the polynomial of order 0, 1, 2, and 3, which means I'll need to find those derivatives. And I guess they wanted me to do it of 0 up here too, so I should have done that. 0, and that would be equal to just this e to the x, that function value, and that would have just been 1. So now I'm going to do this for the others. I got to find those derivatives and the function values at those places. For this approximation, I am going to let a equal to 16 because it's a convenient square root. I know the answer to that, and so I will find f of 16, f prime of 16, and so forth. Now I found those function values. Now I'm going to find each of those polynomial functions, and our very first one is just the solution to square root of 16, which is 4. This one is going to be the previous one, plus I'm going to take that function derivative, which is 1/8, and that would be over 1 factorial, which I didn't really need to do, and then x minus 16 to the first, and then you're going to compute all the way down from there. Alright, and when you plug that into your calculator with your x being the 18, then what you get is the square root of 18 gets closer and closer, as in gets larger, as you can tell by the fact that the error is decreasing. So if you'll see right here, it gets really close with n equal to 3. Next up, we're going to define remainder to be our actual function value minus our approximation. So that will be defined as the remainder for, whichever. You'll have a remainder for 1, a remainder 2, a remainder 3, and if you'll notice in this theorem here, we have our definition for that remainder. For example 5, we're going to find the bound for our remainder. By definition, here's what the remainder is. We are centered at 0, and I know that because we're looking at this function f of x as cosine x, I have this bound of 1 because all of my derivatives are going to flip-flop between sine and cosine and positive and negative. So it's going to be positive negative 1. So I could look at this remainder, the absolute value of this remainder, as being less than or equal to some x to the n plus 1 over, my a is 0, notice, n plus 1. And this is what my remainder would be, since my m is 1. Alright, now it doesn't really matter which derivative I pick, it's still going to be e to the x. And so with that, I've got to find some sort of bound, and I know that it doesn't matter which n I pick. Since that derivative is e to the x, I know that this is really going to look like some e to whatever c that I pick here over my n plus 1 to the x to the n plus 1. Now I need to pick a constant that is going to be less than what my x is, and my x happens to, in this case, be 0.45. So I need to get some value that is less than that. So in thinking about what I want my m to be, I could say that e to the 0.45 is definitely less than e to the 1/2, or 0.5, and that's going to be less than 4 to the 1/2, which I know the value of because this is 2.71 something and this is 4, so I know what this value is, and this is a 2. So I'm going to choose my bound in this case to be 2. That means that my R6, which is what they're wanting me to find, of 0.45 is going to be less than 2 times 0.45 to the 7th, because this is n plus 1 over 7 factorial. And if I crunch these numbers, I get 1.5 times 10 to the minus 6. In using that, I can say that P6 of 0.45 is the sum of k equals 0 to 6 of 0.45 to the k factorial. And this equals 1.5683114, and we can say that the error for this polynomial approximation does not exceed this value. And this concludes 10.1.